Welcome guys. So this video, let's talk about these two integration. So these are also similar famous complex analysis integral, similar as Francis. Okay, so before I start, I hope you guys subscribe to my channel. Okay, so somebody says that creating YouTube channel has to be consistent, right? So I already post like 800 videos, and I still cannot get 1,000 subscribers, right? But don't worry, this will not stop me, right? So I will try to make the mathematical video until the final day of the YouTube. Okay, so let's start. Let's talk about the two methods. Oh, by the way, I have a complex video list, a complex contour integral video list. I will post a link below. So if you like to see me compute other spatial integral, that you can check it. Okay, so let's talk about the method one. Okay, so usually the simple idea is that to connect what you learned before. So it's like you already know some famous integral, and then you try to connect. Okay, so the idea is that let's say y to square x, right? So let's say we solve the first one. First one, right? We got this one, right? So this is the change of variable. Okay, and this guy can be written as two real parts of 0 to infinity exponential minus y squared plus iy squared dy. Okay, and the famous results is the Gaussian integration. I guess everyone knows about it. If you don't know about it, I will post a video link called gamma function, so that you can check about the video list. Okay, so it's a real part from 0 to infinity exponential minus y 1 minus I, right, dy. So a, right, a is just 1 minus I, so this is just what, right, 2 real parts half square root of pi divided by 1 minus I, right? So now there is a problem here, saying that we need to take a square root of complex number. So the problem is that if you take a square root of complex number, there's a usual like 2 number, right? It's not guaranteed that what you get. Okay, so right, so let's see. So let's see 1 minus I is just 1 plus I, right? So half. So this is exact, right? And then if you take you can write as exponential I pi divided by 4. Because cosine pi over 4 is 1 over square root of 2 plus I sine square root of 2. So if you take a square root, then you should get this answer, or pi divided by 8, right? You should get plus or minus. But the problem is that if you I mean, this is a good exercise for you guys to check that this integral should be positive, right? The reason is that when x close to 0, then the cosine will be positive, and the square root will be positive, and this will be positive. And it's obviously that when x close to 0, this term be positive, and this is a greater than when x goes to infinity. So when x gets larger, then the square root gets larger, right? So the total term gets smaller. So even if it has a negative term, the negative contribution to be less than the positive. So this term and this term should all be positive. Right, so once I know this, then I'm very okay to choose this guy, right? So the answer will be 2 times a half times the square root of 2 square root of pi. Yeah, and exponential I pi divided by 8. Okay. So you just take you take the real part of this. Right, so the answer will be cosine pi divided by 8. Okay, and we have a formula that says that cosine theta divided by 2 can be equal to plus or minus 1 plus cosine theta divided by 2. So cosine pi over 8 will be plus or minus square root of 1 plus cosine pi over 4 is 1 over square root of 2. So you can write down as and it's positive, right? Because pi over 8 is less than 90 and greater than 0, so positive. So it's a square root of 2 plus 1. Okay. So plug this in. Okay, so plug this in. you get the finally answer. So our original integral will be, let's say, so to cancel square root of, pull out square root of 2. So I guess finally the answer is this. Let's check it. So this is cosine right, cosine pi over 8. Let's see. So square roots. Okay, so you times the square square. So this is one correct, and then you get a square root of 2. So it's 2 2 2. Yeah. So this is correct. Okay, and the same reason you can change the real part to imaginary part, right? So the same technique gives you the answer. It's the same square root of pi divided by 2 square root of square root plus 1. Okay. Okay, so we're happy. The next is that we use a complex analysis to solve it. Okay. So let's go this way. Maybe we squirrel. Okay. So the goal is to use the method 2, complex analysis. Okay. So I'm sure that everybody knows about residue theorem and the Cauchy theorem. If you don't know, then maybe you should go to my other video. I will put a playlist below so you can check and then know what you should learn. Okay. So let's consider f of z to be let's say exponential. I would choose exponential z times exponential ic divided by square root of z. And I choose a beautiful contour from this to this, and the contour should be choose to this way, right? So this, and notice that you have a square root of z, right? So you should have a branch cut, right? So I choose branch cut to here. So however, right, branch cut will not affect our answer. And then let's see. Let's see. This is A B C D. So I choose A B C D. A B C. Okay. So let's see. Let's change a little. So the problem is that the z has a pole here, right? So we should pick a contour which is which looks like this one. So this is not full one, right? And this is epsilon, and this is r. And then we will take infinity, and epsilon goes to 0. Okay, so we have a full line, right? So we have A B B C C D D A. Integration of f will be 2 pi I residue, right? But there's no pole here, right? The only pole is here. Okay, so we have this. Okay, so the goal is to write down every integral a b c d a b b c c d and d a and see what we get. Okay, so yeah, let's do it step by step. Okay, so first one is a b, right? So a b. So I would that, so a b f of z dz. So AB is a straight line, right? So z should just equal to x, and then from epsilon to r. But at epsilon goes to 0, r goes to infinity. So this is a 0 to infinity, right? Just a standard one. But I can write exponential I in cosine I sine, right? So yeah, maybe we just put in here. Okay. Okay, and the next one is that z equals to r exponential I theta, which is a arc, right? But I don't want to calculate, but you see there is a, so let's estimate the magnitude of f of z. Let's maybe check here. So the second is that the estimate the magnitude. So if I want to do the integration and the z goes to r exponential I theta. By the way, this angle is pi over 4. Okay. So this r exponential I theta will get me what? Will get me exponential minus I 1 minus I r exponential I theta. R exponential I theta I d theta square root of r exponential I theta. Okay, so and you see the magnitude of r comes from here, right? So there's r, and this is square root of r and exponential r, right? So obviously, then when r goes to infinity, this exponential r will decrease more faster than polynomial, right? So this term should be 0. Okay, so it's yeah, so this is very easy to see that the gray arc will give no contribution. Also, the same reason is that the small epsilon, right? The small epsilon arc will give you no contribution. So let's talk about it. So let's see if you choose z to be exponential I theta, and you put f of z as your integrand, right? So this one will give you some epsilon, right? And then you neglect this I part, and then you talk about the square root of I and the epsilon, right? So these terms look like this. As and epsilon goes to 0, then this term will goes to 1, and the square root of epsilon will go to 0. So this term still goes to 0. Right, so the easy dimensional analysis gives you the great arc and the small arc. Also, both give you 0. So the final part is this A, B, C, A, B, B, C, C, D. Right, I'll give you the CD part. So CD is this. But CD is a line, right, from here. So it's z equals to x times exponential I pi divided by 4. And the x from infinity to 0, right? So let's write down this. Yeah, it's a little bit tricky. So let's see. So you get 0 in R, 0 infinity, right? Because you start from infinity to 0. And the exponential minus 1 minus I, R exponential I pi divided by 4. Exponential I pi divided by 4. Let's say this is x. And dx divided by square root of x exponential I pi divided by 4. Okay, so the final computation is just to compute this. Right? This is a little bit difficult, but if you do it carefully, then you should get this. Okay, so finally is to compute exponential minus square root of x dx divided by square root of 2x, right? So the key idea is that let this to be omega. So the answer will be okay. So the answer will be, let's see. So this term is fixed, and the 0 to infinity exponential minus. So this is omega, and the square root of x is omega, right? So x is omega squared. So you get the square root of 2 omega squared, and the dx. Dx give you 2 omega d omega, right? So 2 omega d omega. So you get the exponential I pi divided by 8 times 2 0 infinity minus square root of 2 omega d omega, omega squared d omega. So this term, right? So this term you just use the same formula, right? So it's half square root of pi divided by square root of 2. Okay. Right, but there's a minus sign here, right? Because this is infinity to 0. Okay, so compare everything. Let's see. So we have this term, right? Add this term. Should be 0, right? So sum of them. Okay. So let's write everything down. So the original term is 0 to infinity exponential minus x ix dx square root of x plus this term, right? Okay. Oh, let's scroll up. Okay. So finally, let's write everything. So this I can write as original one. Right. Minus square root of pi divided by half, right? So I combine these to be 1 to the 4th cosine pi over 8 plus I sine pi over 8. Should be correct, right? So because these two can cancel, so the square root of 2 take another square root of 2 is 1 over 4th equal to 0. So 0 to infinity exponential x cosine x the square root of x equals to square root of pi 1 over 4th cosine pi over 8, and the 0 to infinity exponential x sine x square root of x dx equal to square root of pi 2 1 over 4th sine over 8. Right, so this is the same as previous one, I think. Right, so it's same answer if you start from here. Okay, so yeah, this is my video. So this is I think it's the few final complex analysis video. And the next time we will talk about more exotic one, and we will finish the complex analysis.